Now, we can use these concepts to characterize distributed loads, for not all loads we encounter in this class will be point loads. That is, oftentimes they're distributed over the length or an area of a member. This concept is illustrated below, where we have a distributed load that decreases nonlinearly from point A to point B. Now, it is going to be more convenient for us to express this distributed load as a single equivalent point load that is acting at some specified distance from our point of interest on our body. That is, say we have a distributed load as indicated by a red line with our arrows pointing downward. Now, we want to determine the magnitude of our distributed load, i.e. the area under the curve, the direction of our equivalent point load W, as well as the location along our x-axis of where we would apply this, i.e. x bar, such that when we apply W at point P, some distance x bar away from our y-axis, it will still create the same tendency for our body to rotate as did our original distributed load. Now, to do such, we have to look at how our distributed load acts along our member. That is, we have to recognize that W, our distributed load, is a function of the length of our beam L, where now we can say W is equal to a function of x, and it will have units of newtons per meter. Now note, for this analysis to work, our beam has to be longer than the cross-sectional dimensions. For us to begin, we will look at our load diagram, that is, how our distributed load is applied. This will be of great use in statics too. Now we see in this situation that we have 0 newtons acting at point A and B, and we have some nonlinearity between the two. We'd have a reactionary force at A in the x and y directions. We'd have a reactionary force at B in the y direction. We'll cover more of this in Chapter 5. Now, these two reactionary forces would have to be equal to the magnitude of our distributed load to be in equilibrium. This load diagram will contain all the information that we would need to calculate the load at discrete points over the length of our beam. But we will not get into details of this just yet. Now, to determine the magnitude of our distributed load, let us consider a differential force dW. dW is going to be our instantaneous distributed load W times dx, the length it's acting over. And this would represent a differential area, dA, as indicated by the blue shaded region. Now, the magnitude of our resultant force that would characterize our distributed load as one equivalent point load would be equal to the integral from 0 to L of W dx. To determine the location of a resultant force W, we're going to use the fact that the moment of our equivalent force W about A is going to be equivalent to the moment produced by our distributed load about point A. This is incredibly similar to finding our center of gravity of a body. Now, the moment produced by dW about A, dMA, is equal to x dW. Therefore, we can say our moment about point A is going to be equal to the integral of dMA, which is equal to integral from 0 to L of x dW. And this would be equal to x bar W. This is incredibly similar to finding, say, the centroid of an area, where x bar is going to be our distance from our y-axis to the location where our distributed load will be represented as a single point load. Thus, we can say x bar would be equal to integral from 0 to L of x dW per the integral from 0 to L of dW. And this is simply the moment taken about point A due to our distributed load per the magnitude of our distributed load. Now, let us look at an example of this. Say we have a beam that supports a distributed load as shown. If our distributed load is equal to 1,500 newton meters at point A and 4,500 newton meters at point B, and it varies linearly between A and B, we want to determine our equivalent concentrated load and the location of said load using the centroids of our known shapes. Now, the equivalent concentrated load is simply the area underneath the curve of our distributed load. That is, we can say W is equal to 1,500 newton per meter times 6 meters, which represents the rectangular area of our distributed load, plus the triangular area that represents the triangle of our distributed load, which is 1/2 base times height, which is 3,000 newton per meter times 6 meters. Thus, the magnitude of our distributed load is 18,000 newtons. Now, to solve for the moment about A, we want to look for x bar. And we can say x bar times the sum of our areas is equal to sum from I is equal to 1 to 2 of x bar I AI, where x bar is equal to the sum from I is equal to 1 to 2 of x bar I AI, which represents the sum of our moments about point A due to each of our unique shapes, per the sum from I is equal to 1 to 2 of A of I, our total area, i.e. the magnitude of our distributed load. Therefore, we can say x bar is equal to 3 meters times 6 meters times 1,500 newton per meter. Now, in this formulation, 3 meters is the x bar location of our rectangle, i.e. 1/2 our base. That is representing our load of 9,000 newtons. We add this to the quantity 4 meters times 3 meters times 3,000 newton per meter. This represents the moment due to our triangular shape. Recall the centroid of a triangle is 1/3 our base from the heavy side. This represents 4 meters from point A times the area of that triangle, i.e. 9,000 newtons. And we divide this per the magnitude of our distributed load, which is 18,000 newtons. We find x bar to be 3.500 meters.